Welcome back, everyone. In this video, I will begin the lecture for rates of change. Now, this lecture, pretty much we're just going to be talking about old ideas, but bringing them into a new light, talking about them more specifically in a way that's going to help us when we do word problems in the next couple of sections, and the big one being related rates in a couple of sections. Okay, so the first thing I just want to remind you is what the average rate of change is. It's pretty much the slope formula. The average rate of change of a function from x equals x1 to x equals x2 is given by f of x2 minus f of x1 over x2 minus x1. Now, this is pretty much the same thing as the definition of a derivative. There's just not the limit here, because you can think of x2 like x plus h and x1 like x. If you wanted to go ahead and plug in and see that, this would give you exactly that f of x plus h minus f of x over h. And then what happens is when we take the limit as x2 goes to x1, that's what we call the derivative. But a word we may not have used yet is that the derivative can also be called the instantaneous rate of change. So the instantaneous rate of change of a function f, now that's supposed to say at, not and, at x equals x1 is given by f prime of x1, right? Just the derivative. But if you ever see the word instantaneous rate of change, it's talking about the derivative. Right? Now, as a just kind of a little warm up here, we're just going to talk about a function, compute some average rate of changes, and then compute the instantaneous rate of change as well. The big thing that's going to happen in these next few sections is that some problems you'll be given a formula for. Basically, it's going to be those problems that you wouldn't have a formula already known in your head. But others, you're going to have to use knowledge to come up with the formula itself and then do what it tells you to do. And you can see this one, first one here, there is no formula written in the problem. It says, find the average rate of change of the area of a circle with respect to its radius, r, as r changes from each of the following. So you'll notice they all start at 3, 3 to 4, 3 to 3.5, 3 to 3.1. And then at the end, we want to find the instantaneous rate of change when r equals 3, so the derivative. Now, like I just mentioned, in a lot of the problems, especially when we get to related rates, you're not going to know the formula as far as being given the formula. You're going to have to use the problem, whatever it's asking you to do, to come up with the formula. And you should be familiar with the area of a circle formula. The area of a circle, A, equals pi r squared. Okay, so that's just the area of a circle, but this is the formula we're going to work with. This is pretty much our function, almost like f of x equals pi x squared. But because we're talking specifically about a circle with a radius, it's best to leave it with its actual letters. All right, and what it wants us to do to start, nothing to do with the derivative. The average rate of change has nothing to do with the derivative. So when we compute a, b, and c, we're just computing the function itself and using the formula. All right, so part one here, part A, it says we want the average rate of change from 3 to 4. Well, whenever we do that, we're going to do exactly what the formula says above. We're going to plug in the second number, 4, to our formula. So we get, let me go ahead and just kind of generally write down the formula. It would be like f of 4 minus f of 3 over 4 minus 3. And when I'm talking about f here, I'm just talking about the formula we're using, which is the area, and 4 and 3 being the radius, because that's our variable. We're talking about plugging in 4 for r. We get pi times 4 squared minus, then plug in 3, we get pi times 3 squared over 4 minus 3. And that's just numbers, so we can just say that equals 1. And this is pretty easy to simplify. Actually, pretty much can't be easier because the denominator is just 1. It goes away. And 4 squared is 16. 3 squared is 9. 16 pi minus 9 pi would be 7 pi. And we're not given units here, which means you can't really specify what this rate of change is representing. Is it something to do with meters? We don't know. So the best thing we can do is just write 7 pi. Right. But as far as understanding what this means, pretty much what this means is it could give you a good guess about if you knew the area of a circle of radius 3, to guess the area of radius 4, you would add 7 pi to your answer. Now, it might be perfect, it might not be perfect, but that's the idea of why we do this. Now, the next one, you'll notice here the pattern here is kind of just shrinking this second number closer and closer to 3, and the pattern should reveal itself when we actually compute the derivative in part 3. All right, so part B here, we want to do from 3 to 3.5 at the same exact setup here, except we're going to plug in 3.5 instead of 4. So I'm just going to start at that point. Pi times 3.5 squared minus pi times 3 squared over 3.5 minus 3. Now on the bottom here, we've got 3.5 minus 3 is 0.5. And on the top, probably don't know 3.5 squared off the top of our heads. What you could do is use a calculator, get a decimal approximation. You could also write 3.5 as 7 over 2, because it is. And then when you square that, square the 7 over 2, 7 squared is 49 over 2 squared, which is 4. So this is the same thing as 49 over 4. Then we multiply by our pi. Minus, well, 3 squared is just 9 again, so this is minus 9 pi. And we've dealt with simplifying fractions like this quite a bit at this point. We multiply the top and bottom by 4 to get rid of the fraction inside the fraction there. And this would be 49 pi minus 36 pi, which is 13 pi. And 0.5 times 4 is 2. So when we go from 3 to 3.5, the average rate of change of the area of this circle is 13 pi over 2. And now in the last one, same idea, maybe you want to pause it. The main thing you want to do is get your final answer with the pi in it. You don't want to use your calculator as far as getting a decimal. So see if you can do part C. The main thing probably just going to be the simplification, doing the correct squaring. But for part 3 here, same idea, how we plug in. We got pi times the second number, 3.1 squared, minus pi times the first number, 3 squared, over 3.1 minus 3. And the bottom here, 3.1 minus 3 is 0.1. Now, just like the previous one, you can type this in your calculator, you'll get a decimal, but that's probably not going to lend itself to be very easily switched to a fraction. So you want to go ahead and switch 3.1 to a decimal. And if you're ever in any doubt with decimals, you can always move them to the right. So this would become 31 as long as you divide by 10. And however many spots you move over is how many zeros you add. So if you had to move 2 spots over, it would be over 100. But then we want to square it. And this is much bigger number than 7 and 2, so this would be a little more challenging. Figure out 31 squared in your own calculator. I did it beforehand, and we get 961 over 100. It's, again, not necessarily great, but we want to deal with decimals as long as fractions as long as we can. So this thing is 961 over 100 pi minus, we know this is 9 pi again. And we just simplify the same exact way as last time. We want to get rid of that fraction denominator here, 100. We multiply it by 100. But to keep our thing balanced, we want to also multiply the bottom by 100. And when we do that, 0.1 times 100 is 10. And then when we multiply here, we got 961, the 100 goes away, minus 900, and that would be 61 pi. So this would be 961 pi minus 900 pi, which is 61 pi. And actually that's already simplified. So I'm going to go ahead and kind of write it a little neater. Now, if you're paying attention to the number here, that's multiplying the pi, it's 7 it goes from 7, and then when we go to 3.5, we have 13 over 2, which is 6.5, and then we have 61 over 10, which is 6.1. So it looks like it's getting closer and closer to 6. That would probably indicate that when we do the derivative and plug in r equals 3, it's going to be 6 pi. But let's just make sure. So we want to find the instantaneous rate of change, which means find the derivative when r equals 3. So a prime of r, or one thing I will probably be doing, especially with word problems, is not using the prime notation, but using the other d notation, dA over dr. We want to take our formula here and compute the derivative with respect to its radius r. So that's the key here, why I underline this part at the beginning, is when you do the derivative, it's with respect to r. We got d over dr of pi r squared. And the reason that's so important to point out is when you do this derivative, r matches r, which means there's no chain rule here. We're just going to do the ordinary power rule. The pi would stick around and the 2 comes down, so we get 2 pi. We keep the r there, and when we subtract 1 from the power, it's just 1. So the derivative formula is just 2 pi r. Oops. And now after we've gotten that, we can just go ahead and do exactly what this tells us to do. We got the derivative. Now we plug in r equals 3. The dA over dr evaluated at r equals 3 equals 2 pi times 3, which is 6 pi. So in fact, we would have been right if we just completely guessed it. Now, naturally, if we don't care about the average rate of change of a problem, which we normally don't, we typically care about the instantaneous rate of change, we'll only do this part. But it's good to remember that the average rate of change could be something that's interesting or relevant to a problem that you're doing. So it's just something you would have to keep in mind about that. All right. But like I said, that's just practice with both of those. For the most part, what we want to do in this section is the second part, doing instantaneous rates of changes of particular formulas, doing derivatives, but practice also interpreting them or understanding what's going on in a problem. All right, so now the next section here, we just have a few more problems, and they're all going to be about, we're going to be either given a formula or we're going to have to make the formula like above. That could still hold true, but it's going to be really based on understanding what we're answering. One thing I wanted to bring up just from this question here, it says it's about a tank. It's holding 3,500 gallons of water, and it's draining from the bottom of the tank in 50 minutes. If you're in this exact setup, so you have a tank with water draining, and you know how long it would take to drain the entire thing, then something called Torricelli's law will tell you the volume of the water remaining after t minutes is given by V equals, and for this specific one, it's 3,500 times 1 minus 1 over 50t, and then that stuff in the parentheses is squared. Now, if you're wondering what the second part is indicating here, it says t is between 0 and 50. It's just because we don't like t to be negative. That doesn't really make sense. So t starts at 0. That's really just a common thing because it's talking about time. But it stops at 50 because after 50 minutes, the tank's completely drained and there's no more water to be drained. So the time is only valid, this equation is only valid between t equals 0 and t equals 50. All right, so you wouldn't be asked a trick question here, but if you were asked to find the volume or the rate of change of the volume after 100 minutes, it wouldn't be valid because this is not. In fact, it would just be all 0 because after 50 minutes, there's just no water in the tank anyway. But for this one, if you actually look up Torricelli's law, it's a very generic type of law. We're dealing with a very specific example, which makes the equation a lot nicer. But you can do a lot of things with Torricelli's law. It's all revolved around having water in a tank and kind of getting the water to come out. But this example they have here just on the top of the Wikipedia page, it has a whole bunch of tubes where the water is coming out or being drained from. And ours specifically would just be the very bottom. And you could read through this if you were interested in it. It could probably derive the formula here for you, how it comes up with it, but that's not what we're most interested in. We're just really interested in actually understanding how to do the problems. All right, so that is our formula. Luckily, we were given the formula, so we don't have to come up with it. We just need to answer the question. Part A asks, what is the rate of change at which the water is draining from the tank after 10 minutes? Well, one thing to notice here about your formula is you only have one letter T. So if we're asking for the rate of change, which we are here, it just says rate, but that's the same thing. That's good enough to know. We want the derivative at 10 minutes. Okay, so we want to figure out the derivative after 10 minutes. And because our only variable here is t, that means we want dv over dt evaluated at t equals 10. So that's what we're trying to figure out. But we've got to do the derivative of this thing, and then we'll plug in t equals 10. All right, so the derivative. Once again, I'm going to use pretty much this notation. I pretty much always use this notation for word problems. It's just easier for me, especially if you have more than one letter, which we'll see eventually. It's very important to do this. Well, in order to do the derivative of this, we want to do the derivative of our function. We know that 35 would just stick around. Now, one thing is that we've gone through all the derivative rules. We can absolutely do this derivative, but let's go ahead and just kind of break it down and not jump into it too quickly. So doing the derivative this side, I know I can bring 3,500 out as I did because it's just a number. And I want to do the derivative of 1 minus 1 over 50t, and then that's all squared. Well, one thing you should be thinking about is using the chain rule because we have something squared and it's not just t. But outside of that, you're pretty much good to go. As long as you identify what derivative rules to use and everything, you're good to go. The chain rule says do the ordinary rule, which here would be the power rule. We bring the 2 down. We rewrite the inside, 1 minus 1 over 50t. We subtract 1 from the power, which is just 1. And then we multiply by the derivative of the inside, the thing that's being raised to the second power, which is 1 minus 1 over 50t. And that's not too bad of a derivative because it's just the number, which is 0, and the derivative of a number times t is itself. So this is just negative 1 over 50. So up here we got 3,500 times 2 is 7,000. Parentheses 1 minus 1 over 50t. And this derivative we just figured out is negative 1 over 50. And negative 1 over 50 times 7,000. If you do that out, you actually get negative 140. It works out perfectly. And you still have this 1 minus 1 over 50t inside. All right, now this is the derivative. You could try to simplify it, but I really wouldn't do anything to that. The main reason is actually because this negative sign, what's inside here is always positive based on t, and I'll go ahead and show you the graph of the derivative so you can see that. This negative sign means the derivative is always negative. And this is actually important because if you think about water draining out, the rate at which the water is draining is negative because the amount of water is decreasing. But this is our derivative. Now we're going to have to use it for the next couple parts, which is why I'm boxing it in. It's not actually our answer here. We know to get the answer for part A, we want to plug in t equals 10. So dv over dt evaluated at t equals 10. Just take our formula, negative 140, and we got 1 minus 1 over 50 times 10. And 1 minus 1 over 50 times 10, this would simplify to 1 over 5. We get 140 times, or negative 140 times 1 minus 1 over 5. And 1 is same thing as 5 over 5, so this would be 4 over 5 inside. Got negative 140 times 4 over 5. And now we just want to simplify that. And at any point, if you're not comfortable, of course, doing it by hand, or you just want to use a calculator to make sure, of course, do that. The negative 140 has a multiple of 5 in it, so we can cancel out this 5 completely. And 5 divided by 140 is 28. And we have negative 28 times 4. And what is that? That is negative 112. Now, if you're wondering the units, because we should use the units to finish up our question here, it's the rate of change at which the water, which is in gallons, is leaving. So it's gallons per, and the time unit here is minutes. All right, so apparently what it's saying here is that after 10 minutes, about 112 gallons per minute is leaving the tank. So if you knew the amount in the tank at 10 minutes, and then you wanted to guess the amount in the tank at 11 minutes, you would just subtract 112 from your number. Now, we're not asked to do that for this problem, so we're not going to, but that's how we could interpret this. All right. Now, parts B and C are related to asking about the derivative, but where the derivative is biggest and smallest. And this is really where, if you look at the graph of the derivative, it helps a lot. I want to go ahead, and it would also make sense when you see the answers as well. So this is something that you don't necessarily use the formula for. You don't do it as far as plugging in. But let me go ahead and graph the derivative. It's what I have in the box here, y equals negative 140. And then we have 1 minus 1 over 50t. Oops. Now, if you plug in t equals 0, this is just 1. So we have negative 140 at t equals 0. That means our graph's going to be way down here. We keep zooming out. And you can see here, the y-intercept is negative 140. You also notice that this is the graph of the derivative. Remember that. At t equals 50, that's when it's 0. But that makes sense because at t equals 50 is when there's no water in the tank. So the derivative should be 0 at that point. Remember, everything but not between these two values is not valid. We don't have negative time. We don't have time beyond 50. So if I could, I would just scratch through everything that's not between these 2 points. All right, but parts B and C, you can get directly from this graph. It says for parts B and C, at what time is the water flowing out the fastest? And what time is the water flowing out the slowest? Well, if we think about interpreting this in words, this is where it would really help. I'll bring the graph back in a second. But where it's coming out the fastest is when the derivative is largest. And by the derivative being largest, I mean largest negative, because it's coming out. So it's automatically negative. And then for part C is analogous. What time is the water flowing out the slowest? It's the derivative is the smallest negative. Now I have to specify negative because technically, something like negative 100 is smaller than negative 50. But the bigger negative the number is, the faster it's coming out. So negative 100 would mean you have about 100 gallons coming out per minute. Negative 50 would mean you have about 50 gallons coming out per minute. So it's slower the smaller the negative number is. Okay, but just based purely on that, what we're looking at in between these 2 points is when the derivative is the largest negative. We want that time. Well, that's represented on the graph. That's just the lowest point, which is at t equals 0, because we're starting here, but it just keeps getting bigger or less negative. So the biggest negative is at t equals 0. That means the water is flowing out the fastest at t equals 0. And when is it flowing out the slowest? Well, that's when it's the smallest negative. Well, the smallest negative, since it just keeps getting less and less negative until we get to the end, is actually at the very end, at t equals 50. So the derivative is smallest negative at t equals 50. Now, one thing you could ask yourself is, how would I know this if I didn't graph it? Well, this is kind of one of those problems where you can sort of use your best judgment. The more water that's in there, in the tank, you could imagine, the quicker it's going to come out. And the way I like to think about it is the more water you have in there, the harder it pushes to come out. It's just sort of the same idea as, gravity is really what's pushing it out. And the harder you push on something, the quicker it comes out. Just imagine trying to push something through something else. Like can't think of a good example in my head right now, but just imagine that you were trying to push something out of a hole. The harder you push, the more that comes out the hole. And the basically what the water is on top, the more water there is, the more weight there is, so it's pushing harder. But it could also make perfect sense because at least at the end when there is no water, that has to be the slowest. So it has to be t equals 50. But this is going to be true in general. So if you ever have water flowing out of the bottom of a tank, you have a formula like this. The only things that would change are the amount of gallons would change this number and the amount of time would change this number. The rest of your formula would stay the same. But the time which is coming out the fastest is always going to be at the beginning. The time which is coming out the slowest is always going to be at the end. Now, really, we don't have a way to really quantify this yet. And in fact, even if we had that way, which I'm going to refrain from saying because I don't want to bring up stuff that we're not going to be using yet. But even if we could use that way, it would be really hard to interpret because of what it would actually be. So using graphs, using technology, using your best judgment is a very valid mathematical thing to do. You just have to make sure that it makes sense. All right, but in the next video, I will finish up this section and I'll see you there.